Okay, so let's take a look at another example. A cylindrically symmetric spool of mass m and radius r sits at rest on a horizontal table with friction. So it is at rest and there is friction. With your hand on a light string wrapped around the axle of radius r, you pull on the spool with a constant horizontal force of magnitude t to the right. As a result, the spool rolls without slipping a distance L along the table with no rolling friction. Find the final translational speed of the center of mass of the spool. Find the value of the friction force. Okay, so in this problem, in the notes I use the energy approach to solve the problem. I'm going to try a different approach, basically use kinematics in order to get the answer to part A. So what I'm going to do is, first of all, try to calculate the acceleration of the center of mass. So in order to do that, I have the contact point here, and the first thing I note is, because it's rolling without slipping, it is static friction. And for static friction, I don't know where it should point. I will assume that it points to the right, and maybe Newton's laws of motion will prove me wrong. Okay, and in order to get an equation that does not involve this unknown force of friction, I will take the torque with respect to the contact point here. So I will draw a vector from the contact point to the point of application of the force and calculate the torque. The torque with respect to the contact point C. So this torque is equal to R vector magnitude times T. The angle between them is 90 degrees. And what is the R vector magnitude here? It is capital R plus small r. So this total distance I have here is actually, so let me think about this clearly here. So what is this distance? It is capital R plus small r, right? So it is capital R plus small r times t. What is the direction of this torque? As you can see, it's causing clockwise rotation. In this case, it's a negative torque. So it gives me a negative alpha, which is clockwise. This is equal to moment of inertia with respect to the contact point C times alpha. Now there's no mentioning of the moment of inertia of this. All I know is it's a cylindrically symmetric spool of mass m. Okay, for this one I will assume it's a solid cylinder. The moment of inertia for the center of mass central axis rotations is mr squared over 2. So moment of inertia with respect to the contact point will be I center of mass plus mr squared. I look at the distance between the 2 points, it's r, so it's mr squared. So this will be equal to 3 over 2 mr squared. Therefore, I will find that the torque T times R plus R is equal to 3 over 2 mr squared alpha. So my angular acceleration should be 2t r plus r divided by 3 mr squared. Then the center of mass acceleration will be, because it's rolling without slipping, alpha times r, so it will be equal to 2t over 3 r plus r. And because it's traveling a distance L is 1 over 2 a center of mass t squared with a constant acceleration. I find that t is going to be square root 2L over a center of mass, and the final center of mass velocity will be a center of mass times t, which will be square root 2L a center of mass. So I substitute what I have for a center of mass here. The center of mass final velocity should be square root 4TL r plus r divided by 3mr. So in part B, it asks me what is the value of the force of friction. Well, I can use Newton's second law. Net force in X is force of friction plus T. This must be equal to mass times the center of mass acceleration. So this will be equal to 2T over 3R, R plus R. Therefore, the force of friction will be in T parentheses 2R plus 2 small r divided by 3R minus 1. And this will be equal to T times 2R minus capital R divided by 3R. So that will be the answer. Now, is this pointing to the right or to the left? It depends on the value of 2r minus capital R. So if 2r minus capital R is positive, small r is greater than r over 2, force of friction will be to the right. If 2r minus r is negative, r is less than capital R over 2, force of friction will be to the left. So the sign I have assumed is for force of friction to be to the right, which is what I have taken here, F and T in the same direction. And I have found that it depends on the value of small r, if it is pointing to the right or pointing to the left. Okay, let's move on to another example. A spool of thread consists of a cylinder of radius r1 with end caps of radius capital R2 as depicted in the end view shown in the figure. The mass of the spool including the thread is m and its moment of inertia about an axis through its center is I. The spool is placed on a rough horizontal surface so that it rolls without slipping when a force T is acting to the right. Show that the magnitude of the friction force exerted by the surface on the spool is given by this, and determine the direction of friction. So I'm going to assume, because it's rolling without slipping, first of all, it is static friction. So I'm going to assume a direction for force of friction and then figure out if that direction was right or wrong. So I'm going to assume the force of friction points to the right. Okay, so this is assumption. Okay, now I want to find the value of the force of friction. So I can basically write a torque equation with respect to the center of mass location here, with respect to the center point here. So let's write a torque with respect to the center point C. I will find that the torque due to my tension is R cross T. So I find the distance between the T and the center location is R1. So it's T times R1, and it is causing a counterclockwise rotation, R cross T, so it's a positive torque. And if I take the force of friction to the right, this will also be positive. It is F times R2. So this is going to be equal to the moment of inertia I times alpha. Now at the same time, so these are causing rotations in this direction, counterclockwise direction. Well, if this is going to rotate counterclockwise, as you can see, the center of mass acceleration would be to the left, so it would be negative. Now, if I write the net force on the x-axis, that is T plus F, this is equal to mass times the center of mass acceleration, but I noticed that the center of mass acceleration should be to the left, so it's going to be equal to minus mass times a center of mass, because a center of mass is going to be to the left, so if its magnitude is ACM. And because it's rolling without slipping, acceleration of the center of mass should be equal to alpha times r. So alpha times which r? Alpha times r2. Okay, so I have two equations, T r1 plus F r2 is equal to I alpha, and T plus F is equal to minus M alpha r2. Again, why the minus sign? Because its acceleration is to the left. So T and F are in I hat direction. So if you write this like that, this is minus MCM I hat direction. So that comes from the vector nature of this equation. So if I take the ratio of these two, TR1 plus FR2 divided by T plus F is I minus M R2. The alphas cancel because I want to end up with only one unknown. So I will have, well, this is not capital M, it's small m here. So let me replace this with small m, the given in the problem. Okay, so it's going to be minus T M R1 R2 minus F M R2 squared is equal to IT plus IF. So it is minus M R1 R2 plus M R2 squared, plus I in T parentheses will be equal to F times I plus M R2 squared. So I will find that the force of friction is minus I plus M R1 R2 divided by I plus M R2 squared. So its magnitude of the force is I plus M R1 R2 divided by I plus M R2 squared T, but direction I have assumed it is pointing to the right, but I got a minus sign, so direction of friction to the left. So I was wrong in my assumption. Okay, let's move on to another example. We have, I don't know what this is, maybe it's a disc or a cylinder, probably a cylinder, which has an extension on one side, so it's touching the surface in the central cylindrical region. It has mass m, moment of inertia I, and the contact point has no acceleration. The acceleration is 0. The problem is asking me what is the acceleration of point H. So this is under the influence of a force F. Okay, and it's in contact with a rough surface, and there's going to be a friction at this surface. So what contributes to the contact point acceleration? So let's think about this. There is the center of mass acceleration, and there is the acceleration coming from the rotation. Okay, so if I write the acceleration of the contact point C, it's going to have a contribution from acceleration of the center of mass. All right, and then because it's rotating like this, it has a negative contribution minus alpha times small r from the rotation. So if I add the two acceleration vectors, I will get the acceleration of the contact point. And this is 0. So basically it's telling me that the center of mass acceleration is alpha times small r. Okay. Now I would like to determine the force of friction, because it's unknown, and in order to do that I'm going to use Newton's second law. Net external force in the x direction is F minus force of friction. Okay. Now, since the contact point acceleration is 0, that means the contact point velocity is a constant, right? So this is actually not rolling without slipping. There is slipping in this case, backward or forward. Now, and if the center of mass acceleration is greater than alpha r, the center of mass acceleration will be to the left in this case. Then I would have the contact velocity to the left, and the force of friction would be to the right. If it's the other, if it is in the other direction, then it would be the opposite force of friction. Okay, so I'm taking the force of friction to the left. And let's see what happens. F minus F is equal to mass minus m times the center of mass acceleration. So this is going to give me F minus F is equal to, or F minus capital F is equal to m times alpha r. So I will find alpha is equal to F minus F divided by m r. That's my angular acceleration. Now, if I write the torque with respect to the center, the net torque with respect to the center point C will be equal to I times alpha. So this is going to give me F times R, that is clockwise, and small r times F counterclockwise. This is equal to I times alpha. So that will determine alpha. So alpha in this case is equal to Fr minus F small r divided by I. So basically I'm also taking alpha in the counterclockwise direction. Okay, so these two should be the same. F minus F divided by mr is equal to Fr minus Fr divided by I. So if I solve for force of friction here, it's going to give me IF minus I capital F FMRR minus FMR squared. So this is Fi plus mr squared is equal to FMRR plus I So the force of friction is F times I plus mr divided by I plus mr squared. So the force of friction I have found here is positive, so it is going to be to the left as I assumed it to be. Now, acceleration of the point H, AH, is going to have a contribution from the center of mass acceleration, and it's going to have a contribution from the rotation. So it will have a component tangential acceleration alpha times r and minus the center of mass acceleration. So it's going to have alpha times r minus r. Since I have already calculated the force of friction, I can use that in order to find what alpha is. So I can substitute for force of friction into one of these equations. For example, I can substitute it here, and then I solve for alpha. So if I solve for alpha from this equation, let's do that here. Alpha is equal to the force of friction F times I plus mrr divided by I plus mr squared. The force of friction times 1 over mr minus F over mr. Okay, so alpha is going to be equal to 1 over mr parentheses Fi plus F mrr divided by I plus mr squared minus F. So 1 over mr Fi plus F mrr minus if minus mr square f divided by I plus mr squared. So alpha is 1 over mr. Fi's will cancel. F mrr minus mr squared f divided by I plus mr squared. So I can probably multiply this by 1 over mr. It will give me a simpler answer. It will be fr minus f small r divided by I plus mr squared. Okay, so it will be f times r minus r over I plus mr squared. So I can substitute this here. So this will give me alpha times r minus r. So it's f times r minus r squared divided by I plus mr squared is acceleration of the point H. Okay, let's move on to another example. So here I have an object which is inside a moving car that has acceleration a. This is rolling without slipping, and it has moment of inertia I don't know what it is. So I want to know what is the acceleration of this object and what is the force of friction, direction of force of friction. Now, because I'm in an accelerated reference frame, non-inertial reference frame, there's going to be the ghost force ma that's pointing to the left, and I'm going to assume that the force of friction will be to the right. But this is static friction, right? So I'm not exactly sure. I know it's parallel to the surface, but I don't know if it's pointing to the right or to the left. I will assume that it is pointing to the right. And here I can look at the net force on the positive x direction. Net force in the positive x direction is, with my assumption, force of friction to the right minus ma must be equal to mass times the center of mass acceleration a. So I don't know what it is. That's one equation I can get. In order to eliminate the force of friction from this, I can use the torque with respect to the contact point, or I can use the torque with respect to the center, okay, so the center point. So let's take torque with respect to the center. Then I will have the torque equals, let's say that this has radius r here, F times R, and it is causing what kind of rotation? Counterclockwise rotation. This is equal to the center of mass axis, an axis going through the center rotation, so it's the I times alpha. So that's one equation I will get, and so this alpha is equal to Fr over I. Now since this is rolling without slipping, I will have the acceleration of the center of mass is equal to alpha times r, so this will be equal to Fr square over I, right? So going back to this equation here, F minus ma is equal to mass times acceleration F r square over I. I will find that F times 1 minus mr squared over I is equal to ma, and F will be equal to ma divided by 1 minus mr squared over I. So I have to be careful with the direction of acceleration here. So actually this is not right. Why is this not right? Because I have taken force of friction to be positive to the right, F, ma is to the left, and this acceleration that I will get at the end will be to the left, because the center of mass acceleration will be to the left. It will be rolling backwards. So there should be actually a minus sign here. So this is F I hat minus ma I hat minus ma I hat. So you have to be careful with these directions. So I just realized that there is this problem. So what I'm going to do is I will go back to this equation again and substitute alpha is equal to Fr over I, but this time pay attention to the direction of acceleration. So what will happen in this case is F is in positive x, ma in negative x minus ma is equal to minus m alpha r. So this is going to be equal to minus f m r squared over I. So you can see how important it is to pay attention to the directions in these equations. So these equations are all vector equations, so we have to make sure that everything is direction-wise consistent. Okay, so with this correction here, I have I times F minus ma is equal to minus f mr squared. So in F parentheses I have I plus mr squared is equal to ma, and the force of friction is ma divided by I plus mr squared. And this is positive, so it is to the right. So I have found a positive answer, therefore it should be to the right. Okay, and I want to know the acceleration. Since alpha is acceleration is equal to f times r squared over I can just substitute for f. So it's ma over I plus mr squared times r squared over I. So this will be ma r squared over I squared plus I mr squared. So in order to have this or check the dimensional consistency of this equation, what I would like to do is multiply the top and bottom with 1 over I. So I will have a mr squared over I. Here I will have I plus mr squared. So here I have I should have the acceleration unit, but it's not the acceleration unit right now. So I want to go back and check if there is a problem with my force of friction. It's ma over 1 plus mr squared over I. That's correct. So when I used the acceleration here, acceleration is alpha times r, fr squared over I. So I should have for the acceleration force of friction ma over I plus mr squared times r squared over I. So this should be right. Where did I make a mistake? So we have to figure that out. So let me make this divide the top and bottom . Maybe I have made a mistake here. That's right. So that there's an I here, right? Okay. So you can see that because of this I at the bottom, when I multiplied it with f and ma, so I have made a mistake. It's if minus ima is equal to minus f mr squared. So it's this is going to give me an I at this on this side, and this will give me an I on this side. You can see here I have found out there is a dimensional inconsistency. This cannot be right. So I have found out that I have made a mistake. So I go back and do this calculation again with the correct force of friction. And I could have realized this mistake by dividing the top and bottom with I, 1 plus mr squared over I. So this has the right dimensionless quantity. This is dimensionless. F equals ma divided by a dimensionless quantity that has the unit of force. So this is the correct answer. So if I go back to my acceleration here, this is ma divided by 1 plus mr squared over I times r squared over I. So the acceleration will be mr squared a divided by I plus mr squared. And if I divide the top and bottom with mr squared, I would get a I over mr squared plus 1. Again, acceleration divided by a dimensionless quantity. So dimension wise, this is correct. It is a divided by 1 plus I over mr squared. Okay, so you can see the dimensional analysis really helps you figure out if you have made a mistake in your final answer. So there are two things to pay attention to here. One is that vector nature of these equations. So you have to pay attention to, is this acceleration positive or negative? So when you consider your alpha and a relationship, you have to pay attention to this a. So here this a is negative, so that means the acceleration of the center of mass should be to the left. Therefore, I have modified this equation to be minus ma I hat. The other thing is when you're doing these calculations, you can make mistakes like I did just now, and you realize that the answer is not right if you do the dimensional analysis. So by dividing the top and bottom with mr square here, I can see that this has the unit of acceleration. Okay.